This talk deals with operations management. Now, it's one talk in a whole series on this topic, and needless to say, this should all be looked at and studied and thought about in order to get a fuller picture of what this important area is about. However, to start, operations management is simply the transformation of inputs into outputs. It's important that management deal with the transformation of inputs into outputs in an efficient manner. So it takes raw materials or components or whatever, and it uses a combination of labour, capital, land, and resources, mental resources, to convert the inputs, let's say the raw materials, into outputs. Needless to say, that could be done efficiently or inefficiently. So operations management focuses on carefully managing the processes to produce and distribute products and services. Operations management is dealing with the efficient transformation of inputs into outputs. So production is simply the creation of goods and services, and operations management is the efficient production of goods and services. Now, there are significant events in the development of this topic, and we'll just run through some of these to set the picture. As I said, there are several videos on this topic. This one will help set the picture. I suppose really the starting point is the division of labour, which was discussed by Adam Smith in 1776 in his book The Wealth of Nations, or given its full title, An Inquiry into the Cause and Effects of the Wealth of Nations. Adam Smith talks about the division of labour. We have the division of labour in society. Some people are school teachers because they're good at school teaching. They're no good at fixing the car. We have car mechanics who are excellent at fixing cars, but are no good at teaching in schools. So we allocate ourselves into particular occupations depending on our expertise and our abilities. So we have the division of labour in society. We also have the division of labour in a smaller sense. We divide up production in ways that we can optimize the use of resources. So it all really, I suppose, started way back then. Adam Smith popularized it. It was around before Adam Smith, but he popularized the concept. Then we have this idea of standardized parts, which came up around 1800. Standardized parts was quite a revolutionary thought, that products could be standardized. Each one looks the same and acts the same and is the same. It's made up from the same components and so on. And the inputs were standardized. We have scientific management, Taylor. The idea of measuring inputs and measuring inputs against outputs and structuring production in scientific ways in which workers could be controlled and measured and inputs could be measured. So a topic unto itself, and is dealt with in other parts of the course. We also had the coordinated assembly line. Fords did this, where they produced a Model T Ford, and the assembly line was the car moving down the line. As it moved down, workers added more parts to the car. So it was a coordinated assembly line. Then we have Gantt charts, which enables us to measure the progress of projects and set out project schedules and timings. And we had motion study by the Gilbreths in 1922, where again there was an effort to try and measure inputs and standardize the inputs and look at the way work was conducted and try to be more efficient about the way work was conducted. There are lots of criticisms of all of these, and they're all topics unto themselves. But for the moment, in terms of operations management, these are various phases, important phases, that we've gone through. And of course, the last one, the Schuhart's quality control. And if you look at the list, they're still around. We still use Gantt charts. Quality is probably more talked about nowadays than it's ever been, and the need for quality. We still have standardized parts, the division of labor. We still have talk about scientific management, even though many more enlightened people say it's too crude a tool. But the idea of measuring inputs and outputs and designing the workplace, it still lingers on. Methods in operations management. Well, we have the critical path method and PERT, the project evaluation and review technique. We'll come back and have a look at what these are, but that's one technique that's used. We have the materials requirement processing, requirement processing. We have computer-aided design, flexible manufacturing systems, and computer-aided manufacturing, or computer-integrated manufacturing, I should say. So we have different approaches and different methods that can be employed throughout the operations management approach. Let's look at each of these in a little bit more detail. We'll start with the critical path method. Now, this is a tool to analyze a project to determine its duration by determining critical paths through the activity of work. When work is set out, it can follow a network, it can follow different routes. It could be processed on one machine or alternatively processed on a different machine. It could move from one machine to another machine, or it can move in various ways. It can be initiated at different stages perhaps, finally being assembled somewhere else. There are various paths that activities can take. And what this technique does is it tries to chart out the various routes work can pass in, and tries to find out which ones are critical and what's the best route from start to finish. What's the one that optimizes the system? Now, I'm not doing a lot of justice in what I'm saying here, but it's a feeling for what the technique is. The technique is trying to optimize the route in which the work travels through the organization. It enables management to vary the project duration. So it's possible for management to intervene and to select particular ways of doing the particular tasks, particular routes, in other words, through the network. It may accept or reject particular ones. It's collecting the figures that enables the management to make these decisions that really is the problem. And that's the crux of the matter. The activity times are assumed to be known with certainty. But of course, in the world in which we live, activity times may vary because one operator is faster than the next, or one machine is more capable than the next machine, and so on. So activity times are not always known with certainty. Despite having said that, it's a widely used technique and widely respected technique, and one which deserves its own class, which indeed there is. So that will be dealt with in a separate class. PERT, the project evaluation and review technique. Well, this is related to the Gantt chart, setting out tasks, looking at how tasks are coordinated when one task finishes and the next one starts, and looking at slack in the system to see where there is the capacity to do more and move work around to exploit the slack that may be in the system. So Gantt is It's a chart, so it's very pictorial, but it enables management to see at a glance what's happening, what's critical, where the work has got to, what's happening. It's a very visual approach. It allows for randomness, and that's the difference between this and many of the other techniques. We don't always know when projects are going to be completed. The world in which we live have got uncertainties. Things happen. Machines break down. Workers are off ill. Things happen. Companies promise deliveries, supplies, and they don't arrive. So what happens is we may fix several times for each activity, and this variation is considered to be more realistic. We could set times. We can imagine that some tasks will take longer than others, and we can imagine the times that they will take, and we hope that it'll be met within that time frame and the next task can start. And through this process we try to optimize the system. The material requirement processing. Well, this approach tries to meet three objectives. Have materials to meet production requirements and thereby meet customer orders. So that's really an essential requirement. Material requirement processing, it must try to ensure that the materials meet the production requirements, and the production requirements, of course, are aimed at meeting customer orders. It also should try to minimize the amount of materials that are held in the stores. Material held in stores is dead cash. It's not doing anything. It's not helping the business. It's not easing cash flow. It's not making life easy. Materials and components held in the stores are just sitting idle. They are a drain on resources. They are, if you like, an investment, but there's no payback because they're idle. They're sitting in the stores. So the idea is to minimize the amount of stock holding and try to optimize production, delivery, and purchasing. So it tries to get the maximum out of the resources that the company has at its disposal. It tries to meet delivery times and also tries to ensure that purchasing is timely so as to minimize stocks in the stores. But it also that the purchasing is well negotiated. Good contracts are struck and the cost of purchasing is kept down. The material requirements processing takes in information from the bill of materials. The bill of materials is what's required to make the job. So a company who receives an order to make something will have a bill of materials. The bill of materials will specify what's required. Ideally, it should specify everything that's required, every nut and screw and component and piece of metal, piece of wood, whatever it is. Everything should be specified. So the bill of materials, the independent demand, i.e. the final demand from the customers, it is the demand that is outside the business. So it should look at the bill of materials, what do the customers want, and then try to break it down into what does the business have in order to meet that requirement, to meet the order. The independent demand, i.e. the demand for components within the business, well, these are necessary to make the final product. So there is a dependent demand. Now the dependent demand means these are the components and the issues that are needed. So when we think of the bill of materials, we think first of all of receiving an order. The customers place an order. Now, as to whether they place the order or not is outside of the company. that decision to place the order was outside of the company. It's independent demand. But once the order has been placed, then there is a demand inside the organization for the nuts, the screws, the components, and all of the bits and pieces that go to make the product that's demanded by the customer. So we can see two types of demand: independent, which is really the customer deciding outside of the organization, deciding to buy or not buy the particular product. But once the decision is made to buy it, then of course the company must make it and must be in the position to replenish stocks if the order, if the item purchased was out of stock, then the company would want to replenish the stocks. But it has a dependent demand. To make that product, it has a demand for components, raw materials, labor, and so on. So two parts, two types of demand. Computer-aided design. Well, software and facilities that are electronic can be brought to bear on the development of efficient drawings and specifications of components and final products. In the past, draftsmen, using traditional tools, straight lines and curves, would draw out the products. Of course, it was a time-consuming exercise. Now, with computer-aided design, computers can design the product very fast and also ensure that all the parts fit and that it's logical and that the tolerances that have been entered are feasible. So it can render the final image and rotate the image and show what the final product will look like. A lot more sophisticated than in the past, and also a lot more efficient. Flexible manufacturing systems. Well, manufacturing systems that have flexibility built in. Flexible manufacturing systems could be ones in which machines can be turned over from one line of production to a different one very easily, and the workers have the skills to change over from making something to making something else. In fact, there are two types of flexibility. There's machine flexibility, capable of producing new products and changing design requirements. So it may mean that certain parts of the machine have to be changed. New tools may have to be put on the machine to enable it to make a different product. But the machine is flexible enough to do so. So that's one type of flexibility. And the second type is what's called routing flexibility. Selecting between various machines that are capable of performing the same operation. So if machines can do essentially the same thing, then it's a question of finding which one is best. If the organization can produce a certain product, which route through the organization should be used? Which machines? Which personnel? How should the product be produced? So it's marrying up the requirements of the customer together with delivery date, marrying up those requirements and looking at what resources are available and plotting out the most appropriate route through the organization to make the product. Integrated manufacturing, computer integrated manufacturing. This is using computers to control the entire production process. Many companies may have computers controlling particular parts of the production process. For example, some drilling machines or milling machines may be operated by computers who know exactly what the tolerances are and where to make the cuts and where to process the materials. And those would be controlled by computers, but they are in a sense standalone. So there is a computer controlling a machine. It's also possible that the whole plant, all of the machines, since they are computers, they're networked, so that each part of the network can be monitored by technicians and by engineers and by the clever people who deal with these things, who can monitor the whole system. It's like a local area network. This would make manufacturing faster and more accurate. Faster because there's no uncertainty about where the job goes next. There's no negotiations to be conducted. When the job finishes one machine, they don't have to try and find where's the next machine that it's going to go to. It's all planned. The computer knows exactly where it's going. And it's more accurate. The work itself is accurate because the machines may be monitored by computers, and the computers know where the work is going to next. So it's much faster and much more accurate. And it's a closed loop system. Only get data internally, so it can't be corrupted. It's inside the factory. The factory contains all the information. It contains the machines and the computers and the data and the algorithms that the computers follow. It's all held internally. It is not open to wider sources of data. It gets its data from the sensors in real time. So if it's a milling machine, there will be sensors which will tell the machine the thickness of the metal and the surface of the metal and so on, and it'll know how much to cut, it'll know how much to process, because the sensors will determine it. Components of computer integrated manufacturing. Well, there must be appropriate data storage. The programs that the machines use must be stored somewhere. They must be stored on some media, hard drives or solid state or whatever it is. And there must be monitoring, and there must be interrogation facilities. So even though the computer system can be quite widespread throughout the factory and integrated, it still sometimes needs to be monitored. It could be just a security thing that people have, that somehow we like to see a human being watching the machines to make sure the machines are doing what was required of them. I suppose more importantly, bugs can creep in. Even though if it's a closed loop system, the chances of a bug are fairly small. But there might be a bug caused in the programming of the software, which hasn't manifested itself and only under very exceptional circumstances will appear. Well, if it did appear, it needs to be monitored. It needs to be checked. And also, management may need to interrogate the facilities to see where jobs have got to and what's planned next, and if the material is available, and management need to check that the system is running as planned. After all, the management may need to link with the customers or with warehouses or with stockists outside of the factory, outside of the business, and people like to deal with people. Sensors and data input devices are very important in integrated manufacturing, computer integrated manufacturing. Sensors mean that the machines are able to determine what the job they need to do is. If the job requires a certain specification, the sensors tell it what it's got at the moment, tell it what is required, and it will then go about producing what is required. The sensors will very precisely tell it what is required. So it's able to manufacture to a very high tolerance. Software is what drives the system. That's the the other end. The hardware is what does the physical work, the software is what controls it. And the software should be fast and efficient and easy to use. It should be well designed and well laid out. So this has been an introduction to some of the topics that we encounter when we talk about operations management. This is just a brief discussion of some of these topics. There will be individual classes on some of them, for example PERT and critical path analysis and so on, but they will come up more and more in other areas of your study as well, so it's important to be aware of them and to understand what they mean. But that's all I'm going to deal with in this session. I'm going to leave it at that and say thank you for watching.